Hey, bad.
Hey, worse.
Hello.
Hello. In this video, we present a naive solution to the consistency problem. The solution is very simple, but hopelessly inefficient. Our goal is to understand the consistency problem. In an upcoming video, we will explain a much more efficient solution. The consistency problem is this. Given a number of decisions and a set of constraints and a number of truths, find a vector of decisions, or bits, that has the correct number of decisions, that meets all of the constraints, and that has exactly t truths. Each constraint is a pair of numbers ij, which means that decision I and decision j, or both, must be false. Decision I and decision j may not both be true at the same time. When I equals j, then the decision must be false. Here is an example. Say that we want to find 4 decisions where the constraints say that decision 0 and decision 1 may not both be true, decision 0 and decision 2 may not both be true, and decision 0 and decision 3 may not both be true. And we want to find 3 truths. There is one answer, and the result is the vector 0, 1, 1, 1. In this case, there are 4 decisions. 3 of them are true, or 1. And decision 0 and decision 1 have at least one false. Decision 0 and decision 2 have at least one false. And decision 0 and decision 3 have at least one false. Here's another example, very similar to the previous. We are looking for 4 decisions like above. We have the same 3 constraints as above, but we are looking for 4 truths. In this case, a solution is not possible, and so the result will be a null. So why is consistency this particular problem? It is similar to a variety of combinatorial problems, so it is easy to translate from those problems, and it is similar to the fast Hadamard transform, so it is easy to solve. It emerged from our search for a low-level abstraction to solve critter circuit problems. Why does consistency have this name? We wanted to express the notion that 2 decisions either are or are not consistent with each other without stating how. More accurate names for this problem might include simultaneous and NAND. This is our basic function that solves the problem. The 3 arguments, n decisions, constraints, and n truths, are the 3 givens stated above. We will represent the set of constraints as an array of arrays. The outer array contains each constraint, and the inner array contains the pair of numbers ij. The first 2 statements create an array of decisions and set them all to false. The loop repeats until either a solution is found or until all possible decision vectors have been tried. The matches function checks whether all constraints are satisfied. If so, it returns that vector of decisions. The increment function increments the array results as if it were a binary number, and it returns whether or not the number increased. If the increment did not increase the number, then we're wrapping around and no solution will ever be found. The function matches checks 2 things. First, it verifies that the population of the vector equals the number of truths. If not, it returns false. Then it checks every constraint C. If the constraint is violated, if both decisions for constraint C are true, then it returns a false. And finally, if it matches all of the constraints above, then it returns true. The population function simply counts the number of truths in the vector. Incrementing through all bit vectors works a bit like this. It starts with the vector of all zeros, increments it to 1, which increases so it returns a true, increments it to 2, which increases so it returns a true, and so on until it increments it to all 1s, which returns true, and finally, when it increments that vector, it will set all decisions to false, and it will return a false to indicate that it has cycled. The increment function works like this. The loop processes the bits in order from least significant to most significant. This assignment statement increments the next bit. If it was a 0, flipping it increments it to a 1. If the bit was a 1, then incrementing it will create a 2, which is a 1, 0. It will assign the 0 back into that bit and carry the 1 forward. If decision sub I is 0, then the carry is 1 and we need to continue looping. If decision sub I is 1, then the carry is 0 and we can stop knowing that we have incremented the number. And finally, if we loop through the entire array, setting everything to 0, then the function will return a false. The solve function runs in C times 2 to the D time, where C is the number of constraints and D is the number of decisions. And it runs in O C plus D space. Note that this is very space efficient, but very time inefficient.